Optically inspired correlation. Optical computation is the process of using the physics of light, lenses, and filters to provide specific computations at the fastest speeds possible, the speed of light. By modeling light's behavior with mathematical functions, these functions can be performed on dedicated hardware platforms. One such function is that of optical correlation, Kumar, Mahalanobis, and Jude, 2005. The process is shown in. Coherent light is passed through a thin film red-green-blue, RGB, screen called a spatial light modulator, SLM. On one of the set of pixels, assume red, or channel, an image is placed. The coherent light projects this image through lens onto a second SLM. The new image is the two-dimensional, 2D, Fourier transform or fast Fourier transform, FFT, of the image on the first SLM. On the second channel, the 2D FFT of a comparison image is placed and the pixels are individually multiplied. The resulting multiplied image is placed in the third channel and projected by the coherent light through a second lens onto a third lens. This provides the inverse 2D FFT of the combined image, which is actually the correlation. Optical correlation functional flow using an optical correlation device. Function? This will be mathematically described below. For clarity, the input image at the first SLM will be the measured or test image. The image whose 2D FFT is placed at the second SLM is the reference image. As seen in, if the reference image is centered when transformed so that the correlation peak will be centered about the location of the reference image in the test image. In the case of, two copies of the reference image exist in the test image and, thus, two correlation peaks exist. Both are centered about their locations in the test image. This implies that optical correlation can be used for both fast processing and parallel processing, multiple correlation comparisons simultaneously. One problem with the optical correlator is that the SLMs limit the range of values that the image amplitude can attain. The pixels are integer values between 0 and 255. The image at the last SLM is only the real part of the final transform. Also, in some optical correlators, the amplitude of the test image's 2D FFT is normalized to 1, Kumar, Mahalanobis, and Jude, 2005. This is a physical limitation in optical correlators, especially early versions. The normalization of amplitude implied that only the phase information was used. Despite this apparent limitation, this so-called phase-only filter has actually provided improved correlation results. Two correlation peaks are created aligned with the location of the reference image and the input image. The mathematics of the optical physics is straightforward. The standard correlation function between two images phi g is defined as in basic signal processing, Oppenheim, Wilsky, and Hamid, 1996, the spatial or time domain can be computed using frequency domain techniques. The frequency domain version of the correlation function is defined as where fits the Fourier transform. With amplitude information normalized, the POF form of the correlation function based on the optics is. With the advent of faster computers and the desire to avoid using specialized hardware, the optical correlator is rarely used, but the mathematics of the optical physics provides a powerful tool for the correlation problem, which can be applied to the data fusion association problem. For the level 1 fusion problem, the image used for correlation is referred as a tile. The tile is a two-dimensional image that maps data about the target track and the measurement reports into an amplitude plot. Presents an example of amplitude tile. In this case, the tile is 50 by 200 pixel image. The attributes of the target track vector or the measurement vector are the vertical components. The horizontal components are the time reports. Each 10 by 10 block represents a given attribute at a given time. The rows or attributes are defined as target latitude, target longitude, target altitude, target speed, target course heading, target classification. The amplitude tile creates blocks valued between 0 and 255. The columns are these attributes at different times. For amplitude tile, the intensity of each 10 by 10 block is a value between 0 and 255. The range of values for position is limited by the region of interest. This implies that, if the region of interest is for air targets between latitude 32N and 40N and 25E and 33E, Each degree change for latitude, the intensity would change by 31.875 in amplitude, as would each change in intensity for longitude. Similar ranges could be created for the other attributes. The image tiles can be created in a different format. This second 10 by 10 block format is that each pixel of the MNTH block is generated by where mies the number of attributes and niche the number of time steps. The values of eons represent the individual pixel within the 10 by 10 block. An example of a tile from this phase generation is shown in. The phase variations range between 0 and 180 degrees depending on the attribute value. The selection of the phase would be made similar to the amplitude change above. Each attribute has its own frequency as well. This is done to separate each attribute more clearly in the frequency domain.